Good evening. On behalf of the Indiana University College of Arts and Sciences, I would like to thank you for joining us. I'm Vanessa Clow, and I serve as the college's Director of Alumni Relations. Our Food for Thought live streaming series serves as an opportunity for our alumni and friends to hear from faculty experts, explore topics of interest, and stay connected with IU and the College of Arts and Sciences, regardless of your location. At this time, I'm delighted to introduce tonight's featured presenter, Distinguished Professor of Chemistry and a Linda and Jack Gill Chair in Biomolecular Sciences, Richard DiMarchi. A distinguished member of the National Academy of Medicine and the National Inventors Hall of Fame, Professor DiMarchi has dedicated nearly 4 decades to advancing chemistry and related sciences. Formerly serving as Group Vice President at Lilly and later Novo, he is widely recognized for pioneering the discovery and development of transformative diabetes and osteoporosis treatments. With over 100 U.S. patents and more than 250 scientific publications, Professor DiMarchi's academic research in peptides is revolutionizing the treatment of diabetes and obesity. Since 2003, he has co-founded 8 successful biotech companies. Finally, I'm delighted to share that Professor DiMarchi is also a college alum, earning his PhD in biochemistry from Indiana University in 1979. Following his presentation, Professor DiMarchi will be joined by College of Arts and Sciences Executive Dean and Professor of Physics, Rick Van Kooten, for the audience Q&A session. Since arriving at IU in 1993, Dean Van Kooten has served as chair of the Department of Physics and as vice provost for research, working across a campus as a passionate advocate for scholarly activity. He has co-authored more than 750 publications, most in particle physics. As both a scientist and an administrator, Dean Van Kooten is an experienced collaborator, having guided the research directions as physics coordinator of large international collaborations of hundreds of researchers. In his role as the college's executive dean, he remains firmly committed to the importance of a liberal arts education in the College of Arts and Sciences, both for its inherent value and for building the foundational skills of creative, collaborative, and critical thinking and communication. You can submit your questions at any point during this evening's discussion. Simply click on the Q&A tab located in your webinar toolbar. Hover your mouse over your screen and your toolbar should appear. Closed captioning is also available. Now it is my pleasure to welcome Professor DiMarchi for his presentation. Thank you.
Good evening. I'm here in my chemistry office on the 5th floor, and I appreciate the opportunity to present to you this information that has been a big part of my life. I want to thank the dean for the invitation to do this. I want to thank all my colleagues in the chemistry department and in the Gill Center for the support that I receive in doing the work that we do. And particularly, I want to thank Jack and Linda Gill for their persistent support, financially, intellectually, emotionally, in helping us do the things that we have been about. What you should see on the screen right now is a set of molecules. This is my molecular family, entities that have had real meaning for me and things that we have brought to new life in performing phenomenal pharmacology. At the center is a photo of a textbook that Jack Gill had sent to me not long ago from Casey Nicolau and his associate that speaks about molecules that change the world. There are 34 chapters in that text, and 33 of them speak to conventional molecules, small molecules, things that are typically orally administered. The last chapter speaks to so-called biomolecules, large molecules, macromolecules of the type that you see surrounding that particular photo. Glucagon, insulin, Forteo, things, as I've said, that have real meaning to me. It's been a persistent search for these miraculous molecules. And what I show you here in the upper left-hand quadrant is the photo of a young fellow at the age of 5, only 27 pounds of weight, struggling with juvenile onset diabetes. He was fortunate that his parents were connected. His uncle was a physician that had connections to the Banting Best, the now Banting Best Center in the University of Toronto, where he was one of those first children to receive insulin therapy. And it sustained his life. You see him 70 years later in 1992 as he came to visit my laboratory at Eli Lilly as we were progressing to the submission and registration of Humalog, lice-proinsulin, a molecule that I had discovered during my tenure at Lilly. He was the first individual to achieve 70 years of life sustained on exogenous insulin administration. Quite an inspiration. Came with his family, his children, and some of his grandchildren, which just showed you the power of what chemical entities can do. Now, what we do is chemistry, and in fact, the challenge for me this evening is to try and translate this language of chemistry into English and not overwhelm you or intimidate you with the foreignness of what chemists use to communicate with one another. It gives us the ability to control the physical properties of a substance. And in controlling those physical properties, we can bestow upon it biological properties. And what you see here are a number of those classical oral small molecules that would have been in the first 33 chapters of Casey Nicolaus' textbook. But they're relatively small in size and quite exotic chemically relative to what you find in nature. For us, macromolecule medicinal chemistry began in the late 70s and accelerated in the decade of the 80s. And I came back to Indiana from my fellowship at the Rockefeller University on the east side of Manhattan because of the groundbreaking capabilities of using microorganisms to produce these large proteins, right? Using DNA to direct the synthesis of these precious materials. And the first of those was human insulin. Lilly's pioneering work to produce what became known as Humulin. And that molecule was first registered in 82, but distributed here in the United States in 83. And so it was in the late 70s, the very late 70s, 78 through 82, that we did this work in Indianapolis in taking what had been established in California at microgram scale to hundreds of kilograms and then thousands of kilograms, tonnage. It was truly one of the spectacular accomplishments in mind biosciences, and I'm very proud to have been a part of it. I often say that biotechnology became medicine in Indiana, in Indianapolis. That's where these first medicines were produced. And in fact, if not for that accomplishment, we'd probably be rationing insulin today. It provided the unlimited source of insulin. But for me, it was a mechanism to be able to produce molecules that we could modify the sequence. Up until that point in time, insulin had come from the pancreas of animals, pigs, cows. Growth hormone came from the pituitary, the brain of cadavers. And one of the more colorful ones was follicle stimulating hormone, the hormone used to promote fertility. Came from the urine of nuns. It was referred to as holy water. 10 nuns, 10 days, one treatment for a single woman seeking fertility. Biotechnology has liberated us from those materials and all of the exotic xenobiotic materials that they could become contaminated with. And what you see on the right was my belief that we could design these molecules to do something more than nature was designing them to do. Because while physiology and pharmacology are aligned, they're not identical. Nature selects for certain properties and pharmacology selects for others: stability, potency, route of delivery, polyagonism, as I'll show you in a minute. So Humalog was the first in this set of synthetic macromolecular drugs. Now, for those of us that were working on insulin in this period of time, it was quite evident that this explosive growth in the demand for insulin was being driven by something more than just the organic change in genes. This was the emergence of what we now know as the epidemic of obesity. The increased weight places a stress on the pancreas. You're less insulin sensitive, and as a consequence, the pancreas is less able to deal with the demands that we place upon it. And what you see in the face of this one young lady, age 14 at that point in time, on Time magazine, was that she had what we had known as adult onset diabetes, something that occurs with a mean age of 55 years. It's now dropped to as little as 45 years, but we were seeing it in adolescence, and with great concern, because that placed the burden of having to manage that disease for many, many additional decades on top of the risk that excess body weight placed on cardiovascular performance. And the star of the show, Science, the prestigious journal Science, last year described a GLP-1 and these obesity therapies as the breakthrough therapy of the year. Well, I assure you, it didn't happen in 12 months. It reaches back 4 and 5 decades to the incretin hypothesis that we as functioning individuals are sensing the nourishment that we take in the gut to signal to our pancreas to prepare for this extreme nutrient load that we receive roughly 3 times a day, and to signal to the brain that it's time to stop eating. It also signals to other distal organs from the adipose bed to bones and skeletal muscle. And the first of these incretin hormones was a substance called gastric inhibitory peptide that was discovered in 1971 and hypothesized to be of use in treating adult onset diabetes, something that could be used to lower blood glucose without the risk of hypoglycemia as insulin presents itself. It proved to be a failure. The substance did not work in lowering blood glucose in diseased patients. And it was in 1986 that GLP-1, the central ingredient in what you would know as Ozempic, in fact, was described as the chemical substance, the hormone, that was then refined into the drug many decades later. That first cloning of that gene, right, the DNA sequence of that gene, was conducted by Graham Bell as he was leaving Chiron Corporation to take a faculty position at the University of Chicago. And in this seminal publication that appeared in Nature in 1983 is described the gene sequence, and it's shown below in the hieroglyph of what we abbreviate gene sequences with the 4 nucleotides, and then down below its translation into an active peptide. And in the red box, what you'll see is what he discovered is that there seemed to be a duplication of the glucagon gene. We'll talk a bit more about the glucagon as a substance in a minute. But there were 2 additional genes that followed it that had high homology to glucagon itself, approximately 50% conservation of sequence, suggesting similar functions. And Graham hypothesized that it was this 37 residue peptide, starting at residue 1, as you see at the bottom of this slide, as lyse-arginine, a processing site that is commonly observed in polyproteins to generate active peptides, and the C-terminal end with another arginine as a processing site to give you a 37 residue peptide. That's what he believed was the active substance, which turned out to be wrong. In fact, for those who were closest to glucagon, the belief was that it was going to start with this histidine at position 7, and that the active sequence would read from that 7 on, because we knew the structure function of this molecule glucagon began with a histidine and had a glycine, threonine, phenylalanine at 4,5,6, phenylalanine at 22, tryptophan at 25 as part of the active hormone, and it made most sense that these duplicated duplicated sequence would likely conserve those active sequences. And that's what takes me back to my days in New York, where Bruce Merrifield, Robert Bruce Merrifield, going by his middle name, RBM, to those of us who knew him best, developed this orthogonal way to do chemical synthesis of these very substances, to actually do chemistry on a solid support, an insoluble solid support, where most were believing that you could. Truly inspirational fellow who was capable of thinking outside the box. Working alongside me as a fellow on a different project was a graduate student who became a postdoctoral fellow in Bruce's lab, named Svetlana Moishev. She developed the chemical synthesis for producing glucagon, and then went off to the Massachusetts General Hospital, where she continued her training as her husband did his training in medicine. And she was the one who, in producing those peptides and the radioamino acids that actually determined that the 7 to 37 was the active sequence. But unfortunately, through the years, she was forgotten for the seminal accomplishments that she made. And it's only in this last year that we have brought the recognition that she so rightly deserves. And you'll see in this Science article that appeared in September, and later the awarding of the Vin Prize Future Award in Hanoi, that she is now becoming recognized for this important discovery of this particular hormone. Now, the transition to obesity is a different story, because the focus was on glucose control, right, as a diabetes drug, not as an anti-obesity agent. And Suat Efendik was the chief of medicine at the Karolinska Hospital, very prominent medical institution in Stockholm. And he was the person who sort of took me under his wing and convinced me that this had the ability to decrease body weight. And we began a collaboration while I was at Lilly, where I and my associates produced the GLP-1 that was placed into patients, and that led to a patent that was filed in November of 1996. So here we are, roughly a decade removed from when the hormone was first shown to have this incretin activity, the glycemic activity. And what was shown is that over 4 weeks of therapy, where it was subcutaneously infused in type 2 diabetics that were of excess body weight, that they lost as much as 3.5 kilograms of their body weight in that period, as opposed to only 1.3 when they were given insulin. That's the treatment effect. You tend to see that if they had been given vehicle. Actually, insulin tends to promote weight gain, not decrease it. And in this patent that was issued to Lilly 2 months after I left the company to join here in my faculty position at Indiana University, they received claims for reducing body weight with GLP analogs, and GLP derivatives, the whole class of these medicines. There was no interest in developing this substance. The company was focused on neuroscience, Prozac, Zyprexa, Cymbalta, Strattera, fantastic oral drugs, very traditional in their forms. And obesity was not viewed as a disease. It was something that was relatively benign with an unclear registration path. And I was often told, even if there were a path to register it, very few people would be willing to take an injection to treat that disease. That has proven so wrong over the course of the last 20 years. Novo was the one company by exception that embraced this and continued on with native GLP sequence and modified it ever so slightly to place a single fatty acid on the molecule, some very elegant chemistry that gave the hormone the ability to bind albumin and therefore would be injected just once a day. They added one more modification to the hormone, again, reaching back to what I showed you in Humalog, that chemistry matters. And this hormone, when it was administered to patients for one whole year, what they found was that they could decrease the body weight as much as 8, 9, 10%, and the vehicle treatment lost 2 or 3%. So high single-digit difference in your ability to lower body weight. And you'll note at 4 weeks, they lost exactly as much as we had seen in the infusion study with Professor Effendic that served to form the patent that was issued to Lilly. But take note that about a third of the subjects lost as much as 10% body weight, and as few as 1 in 7, 14%, lost 15%. And here we are in 2015, 30 years removed from the discovery of the hormone. The folks at Novo, through some additional elegant chemistry, changed the nature of the fatty acid that bound to albumin. And they also introduced an additional amino acid change to give the hormone resistance against proteolysis. This is the active substance that you know as Ozempic. In fact, registered for treating obesity as Wegovy, but it's the same active chemical entity. Saxenda with liraglutide is the same active ingredient in Victoza, the once-a-day treatment for diabetes, Saxenda, the once-a-day treatment for obesity. But the spectacular finding, and quite frankly, the unexpected finding, was this additional efficacy that has generated this craze for interest in getting access to these medications, where at roughly 1/10 the dose, instead of 3 milligrams per day, 0.3 or 0.4 milligrams per day, as many as half of the patients over a year's therapy were losing 15% of their body weight, and a third as much as 20% of their body weight. The drug is associated not just with improvements in metabolism and body weight, but also a decrease in cardiovascular risk, what we know as MACE, right? Major adverse cardiovascular events, deaths, MIs. And this is a highly meaningful, not just statistical improvement in general health. And it is something that differs slightly within the class of chemically modified GLP-1 agonists, of which Ozempic has proven to be the most superior. Now, here comes the part that relates to our work here in Indiana. I moved again in 2003 when there was little interest in developing these therapeutics for treating excess body weight. And in 2009, working with students here in Bloomington on the 5th floor in collaboration with Professor Matthias Chuck, a physician who I knew from his postdoctoral days in Indianapolis at Lilly, when I was an executive, who had come to take a faculty position at the University of Cincinnati in the medical school focused on pharmacology. And what you see on the right is the leading edge of therapy to treat diabetes, which represents an integration of 3 hormones into a single substance, which I'll show you in a minute. It includes that active ingredient GLP-1, but 2 other active ingredients, GIP, which was thought not to have any efficacy, and glucagon, which was completely countercultural because the belief was that you had to block glucagon as opposed to stimulate glucagon. And that 2009 publication integrates glucagon with GLP. In 2003, in Science Translational Medicine, we integrated GLP with GIP, which is the precedent for what you now know as Mounjaro, Lilly's breakthrough drug. And then in Nature Medicine in 2015, we integrated all 3 of these substances into a single molecule, which I just mentioned to you as retatrutide, real tongue twisters for generating what is a 24% decrease, mean decrease in body weight. That's roughly 1 pound per week for a year, 50 pounds. Incredibly transformative. Now, life in discovery is far more empirical than is often told, and it takes a heck of a lot longer time than might have been suggested, as I said, by the award of 2023 for this hormone and what it's capable of doing. We began with glucagon, not with GLP. And we wanted to do something relatively simple, and that was to generate a glucagon that could be used by someone who is insulin-dependent diabetic, because it is the rescue medication if you have excess insulin therapy. You receive it as a kit that looks something like this, where it is a lyophilized powder. You get an acidic diluent. You dissolve the powder and give yourself an injection while you're struggling with life-altering hypoglycemia. It's not a time when one needs a chemistry kit. What you need is something that looks like an epinephrine pen to immediately administer and rescue you from this hypoglycemic challenge. And so we set out to use chemistry. Here, one of my graduate students, Joseph Shaben, and one of the postdoctoral associates, Piotr Moroz, that have been longtime trusted associates that did just spectacular work, working with one of my longtime colleagues later on, Dr. John Meyer, who's now at the University of Colorado Boulder, but led the Lilly peptide group in after my departure. And what we did is we developed 5 different methods to take a substance that is virtually insoluble in physiological buff and convert it into something that had full biological activity and stability so that it could be used as a medicine. No one at Lilly, no one at Novo, no one at the Juvenile Diabetes Research Foundation was interested in supporting our work. The interesting aside to all of this was when I asked Professor Chuck, here shown as a younger man than he is today, 20 years ago, to administer this to fatty rodents, diet-induced obese mice. They're roughly twice the size of their normal wild-type littamates. It was every bit as effective as Ascendin 4, which is a homologue of GLP-1. So it functions very much like what we later came to know as Saxenda and Wegovy. And what you see in blue is it was every bit as effective in lowering body weight as Ascendin was, but it was doing it by a different mechanism. It was increasing thermogenesis. It was making these animals less fuel efficient, meaning they're burning energy, right? It's like a car that has lower miles per gallon than one with higher miles per gallon. And we asked, could we integrate that in with the food suppressing effect, the appetite suppressing effect of GLP-1? A single molecule that could do both of these things. And in fact, working with graduate students here, Jonathan Day, who's now a senior scientist in the insulin section at Lilly, found that he could make a single hormone that could see both of these receptors, had both of these activities, as if it was a master key, opening 2 doors as effectively as it opens 1 door. And when Matthias placed these into fatty animals, what we found in blue is that they were more effective in decreasing the body weight of those obese animals than just one activity. And they did it without significantly changing the food consumption. They weren't making these animals sick to decrease their body weight, and their lipid metabolism was much improved. Far less lipid in their liver and far less cholesterol and triglycerides in their plasma. And what's shown here by NMR measurements is that these animals had increased their energy expenditure without changing their cardiovascular profile. It wasn't an increase in heart rate or blood pressure that was driving this improved performance. As we shared these results in Nature Chemical Biology, I remember when Good Morning America came here and was filming, and students were running in every which direction, excited. Most viewed this as just rodent pharmacology, and the informed advice we got from opinion leaders was, you're going the wrong way. Glucagon's going to increase blood glucose, and of course, it's going to end up being dangerous. And what we were arguing is that we could use it as a catabolic substance to generate a futile cycle, where one substance is catabolic, one substance is anabolic, and net, what we're doing is decreasing body weight by expending more energy. We then returned to GIP, which was the substance that hadn't worked, and there was great controversy as to why are you wasting your time, because if anything, you might want to block this hormone as opposed to stimulate this hormone. And we were inspired by some work that came out of the University of Copenhagen, where it had been shown in diabetic subjects that if you infuse GIP, their ability to secrete insulin was no better than using saline. It was inactive. That's the reason why people were telling us, don't waste your time. GLP, by contrast, was active, meaningfully active. But if you improved the glycemic state of these subjects by infusing insulin or treating them with insulin for 4 weeks, what you found is that you restored the ability to see GIP and enhanced the ability to see GLP. And so we envisioned that we could use GLP as the first stage of the rocket to improve glycemic control, and then GIP would be able to function. And this is an important observation that was made, again, in Cincinnati. The first author on this paper was another graduate student who, like Jonathan Day, Brian Finnan, was a Gill fellow supported by the generous philanthropy of Linda and Jack Gill. And what you see is when we treat them with GIP alone, they do virtually nothing relative to treating them with vehicle. If you treat them with GLP, they lose body. That's why it's such a magical substance. And through the first days when we treated them with both hormones, they're no different. Again, reminiscent of the fact that you have to induce a pharmacological sensitivity. And with continued time, all of a sudden they started to separate, and to meaningfully separate in a positive direction, such that we went ahead integrating these into a single molecule. And what you see on the left is the single GLP agonist, liraglutide, the active ingredient in Saxenda, in Victoza, at the same dose with these dual-acting compounds. You're looking at the blue. So you could use either a smaller dose to achieve the same effect, less gut side effects, or you could achieve greater efficacy. And indeed, these are the phase 3 clinical registration results from Lilly with this peptide called tirzepatide, which is a once-a-week analog that was developed at Lilly, having seen the precedent-setting direction that we had published upon with GLP-GIP agonist. And now all of a sudden you see that at those higher doses, 3/4 of the subjects are achieving more than 15% body weight, and as many as 2/3 more than 20% body weight, and even as many as a third, 40%, achieving more than 25% body weight. Want to put a face on that? Here, just go onto the internet and Google the efficacy of Ozempic, or certainly tirzepatide, which is now sold for obesity under the trade name Zepbound. Here's a lady a patient in Tampa, Florida, who has lost over 100 pounds. In lecturing at Northwestern Medical School in November, I met what was an individual out of the 100 Club, somebody who has lost more than 100 pounds. She was 53 years of age and still overweight at 190 pounds, but she had lost 120 pounds, 40% of her body weight. And she told me that she can't remember when, prior to her teenage years, she was less than 200 pounds. And so she felt as if, as she said, she had gotten a get out of jail card, that she had been liberated to have a different life than the one that she felt she had been assigned. Okay, so the last of these is these triple agonists, where we then pulled these three activities into a single molecule that could see all three receptors. If I may say so, it's quite an elegant piece of chemistry, because it's very much like a Rubik cube, where you finally get two faces set and go to set the third face and end up destroying the first or second face. And so what we developed were molecules that could equally see these receptors as much as the native hormone did, and they can do it with the same potency that the native hormones see those. And in fact, when we put those into rodents, you could see that the co-agonist, this active approach that is modeled in tirzepatide, but this being peptides we had made at Indiana University and studied at the University of Cincinnati, were phenomenally effective here, losing more than 15% body weight. But adding in the glucagon component, these triple agonists were doubly effective. And what you're looking at here is the fat content, where those white circles are lipid droplets in your liver, which are a risk factor for liver failure, right? Non-alcoholic steatosis. And you can see how much more effective the triple agonist was than the co-agonist. And in June of this year, once again, Lilly presented results with their triple agonist at the ADA meeting. And what you see is that at the higher ends, 2/3 of the patients lost more than 20% body weight. And as many as a quarter of them are losing over 30% body weight. And there was a notable effect in decreasing hepatic lipid content, a very promising observation. Again, this is in registration. It is not yet a approved drug for use. And then lastly, I'll just close with one last piece of chemistry, something a company I started in 2003 that was just recently purchased by J&J for using this chemistry in labeling antibodies with conventional cytotoxics for improving the efficacy in treatment of oncolytic diseases. But in this instance, what we did was take a protein such as leptin produced by biosynthesis and use non-native protein biosynthesis, something championed by my colleague in co-founding this company, Peter Schultz, who's now president of the Scripps Institute, where we could introduce ketones into the molecule, biosynthesize something that just doesn't occur naturally. And ketones have this important chemical property that you can do orthogonal chemistry to introduce new function to a molecule. So it wasn't just like adding letters to the alphabet. This was like adding vowels to the alphabet. You might wonder how powerful would the English language be if you had a sixth or seventh vowel to work with. Kind of a strange question to ask, but you do wonder about these things when you're sitting alone in a building like the chemistry you're building this time of night. But here's a study that was done in those same obese animals when we treated them with pegleptin, leptin being the so-called obesity hormone that was discovered by Jeff Friedman in 1994, which has spectacular efficacy in genetically deficient animals and in humans, had no efficacy in what we call garden variety obese subjects that got there by excess nutrition. When you mix that hormone with one of our co-agonists, you could do this with the triple agonist as well, there's no difference until they lose about 15% of their body. And then all of a sudden, leptin kicks in and takes them back to a normal body. Now, the substance was never developed, and largely because the question at that time was, how would you decrease human obesity by 15%, 20% if it's required in humans? I think that's all mute at this point in time, given the efficacy that we're now seeing with these leading edge peptides and the potential for now integrating leptin to get to, who knows, 30, 35, 40% decrease in body weight, and all of the improvements that means in the comorbidities of the diseases, bone, muscle, pancreas, liver, potentially brain. And so let me close there by just acknowledging the importance of Indiana University. These are the students that did the work here on this campus. And I'm doubly proud because it was done by so many young individuals that were guided not just by me, but the likes of seasoned senior research faculty, Jay Levy, Dave Smiley, Vasily Galvanov, who's right there in the picture. Most of them are employed in the pharmaceutical industry at virtually all of the large pharmaceutical companies that you can envision: J&J, Lilly, Novo, Takeda, and many in Asia. Lian Shenzhang is the CSO of Henri. It's the largest public biotech pharmaceutical company in China. And then finally, the one thing that has inspired me, and I try to instill in all of our students, is the ability to think differently, right? To, as Steve Jobs said, those who are insanely great, that ability to do what others just simply can't see. From Irv Johnson, the visionary at Lilly that started biotechnology, to those seminal Nobel laureates that frequented this campus: Herman Mueller, James Watson, Salvador Luria, right? All connected to one another. Carl Djerassi, the chemist who developed contraception. Brian Malloy, Prozac. And of course, I mentioned Bruce Merrifield, and you'd surely know Maria Callas, Martha Graham, Pablo Picasso, who stimulated our creativity in the way that this campus stimulates my creativity. So thank you for the time. I hope I didn't run too long. And as Paul Harvey used to say, now you know the rest of the story. Thank you.
Well, thank you very much, Richard. And I think on behalf of it, I think there's roughly 115 people out in the audience for just a fascinating talk, and just the level of pride that we have that Indiana University is a part of this life-changing research is just remarkable. So thank you very, very much. So I'll just jump into questions. And again, a reminder to the audience that we're doing it through the Q&A box. You just type your question in there and I'll answer it. I'll ask a question of Richard and he'll respond accordingly. Can you discuss promising treatments for osteoporosis, from Patricia Brennan?
Yeah, so osteoporosis experienced a renaissance through the decade of the 90s as we progressed important therapies for treating the disease. Selective estrogen modulators such as raloxifene, the active ingredient in Avista, and Forteo, a hormone that I was about, which thanks to individuals like Janet Hock, Chuck Froelich, John Termine, I'll miss someone at Lilly, recognized that it could be used as a daily pulsatile injection to build a bone. And it has become one of those first regenerative medicines that decreases the number of fractures that folks will experience in later life. There is still more to be done. And particularly when you think about what might be the effect of excess body weight loss, because excess body weight has a way of increasing bone mineral density. And the fear right now is when people lose as much weight as we experience in these clinical studies, that you'll also be losing bone mass. Yeah. Muscle mass, right? Lean muscle mass is part of that weight loss. And so are we putting people at increased risk for a fracture? Simply because they have less resistance to a fall. And so there is a need for entities that can go beyond what you can do with a bisphosphonate or a glycan inhibitor to achieve safe and effective further increases in bone mass. Associated with that is also the related diseases of cartilage, right? Osteoarthritis and the tremendous growth in the number of surgeries to replace joints, hips, knees. And so can we find anabolic therapy that can rejuvenate the joint and create that collagen that has been lost, that serves as the cushion and leads to so much pain? I think that is all possible, just as we now realize that we can treat obesity when so many thought what we are achieving today to be virtually impossible.
Great, thank you. So from Scott Curnow, are studies ongoing in pediatric patients to prevent development of severe obesity versus treating those adults with severe obesity that already have comorbidities? That's a great question.
Yeah, it is a terrific question. And obviously, if you can prevent a disease and when it occurs, if you can cure it, that would be wonderful. I should tell you that if you stop taking these drugs, very much like if you stop taking your antihypertensive or your statin for lowering cholesterol, your body weight is going to change. What you hope is that this stimulates not just a loss in weight due to the pharmacology, but a change in lifestyle that might allow you to change your diet, to have a more healthy exercise routine so that you can survive with, if not a complete absence of pharmacology, a lower dose. Preventative studies are more challenging, and particularly preventative studies in youth, right? Because there are additional requirements for treating people at these early stages of life. But it's obvious, as I showed you on the face of that one young lady who was on Time magazine, that there is a need. And so I suspect those studies are being done. But I'm not sufficiently integrated into Novo and Lilly at this time to know exactly what's being done. So I can't comment informatively.
Okay, thanks. Christine Alpig asks, first, thank you for your talk. Given the length of rodent studies, how long do you think it will take for us to understand whether people's metabolism converts back or counteracts these medications?
Yeah, so, let me start with, if there's a reservation that I have at this point in time, it's in the popularity of these drugs.
Yeah.
Right. There's only so much that you can achieve in a registration study. And these studies are designed to emphasize the signal relative to the noise, right? Because you need that in order to demonstrate the results to justify the registration. So the folks who have been in most of these studies look more alike than they are different. And as you begin to distribute these drugs, they're being used in a more heterogeneous setting of patients. You've asked about children, right? And you know that despite the fact that they have not been extensively studied as they were in maturity onset adults of roughly 100 kilograms of weight, they are being used. And they're being used not just in tens of thousands of patients, but in hundreds of thousands of patients. And so you learn a tremendous amount as a drug is registered, and the faster it's being used, the more challenging it is to collect all of this data to make sure that there isn't something that we have missed. In addition, there's enormous concern about abuse. People want to lose weight. And so there are some who think that if taking it once a week is a good thing, then maybe taking it every day will be 7 times better. Well, let me assure you,
lose dangerous
that
amounts.
is not the way to do it, right? And so please adhere to the recommendations and work closely with physicians. One last concern that I have is because of the shortage of the drug and the huge need, there is contraband here in the United States that are coming from external sources. I view this as rodent medicine. These are research-grade peptides for which we don't know what the quality is. We don't even know how they've been formulated. It's dangerous to use such substances, and so I caution you, despite the attraction of the pricing or the availability, that this is not advisable.
And this might be answered already. Will these medications have to be lifetime usage so as not to have reoccurrence of the individual's obesity? So you're saying already that if you stop taking it, that your weight could go back up?
It's been shown that upon stopping therapy, the weight does return slowly, but it does return. And so the incentive is obviously to use this to get into a better physical shape, a physiologically healthier state, but to use it as a catalyst for a more healthy lifestyle. There are many people who are significantly overweight that cannot begin to exercise, and in which exercise may be counterindicated because of the strenuous nature of what it represents. And so if you can use this to catalyze a better lifestyle, then I believe you can exist with less intensive therapy. But I suspect you will need to use this as much as you would be using your statin lifelong to keep your cholesterol in check.
Thanks. This next one is I think comes up a lot because people are sometimes adverse for giving themselves injections. So Lisa Houderloot, thanks you for a fascinating talk. I thought I'd heard that an oral treatment for obesity was under development, but given these are all large molecules, I'm wondering if that's possible. Can you please comment?
Well, there's a couple of parts to this. The first one is there is an oral form of semaglutide, right? That's called Rybelsus. And Novo was precedent setting in formulating the peptide so that it could be used as a daily oral medication. It's quite effective, but not quite as effective as the once a week injection. They have now reformulated to be bringing forward a higher dose of the peptide to achieve comparable efficacy. It is appreciably inefficient. That is, instead of using roughly 2 milligrams a week as an injection, you're using as much as 14 or 50 milligrams per day. That's 1 to less than 1% bioavailability. And for some patients who refuse to use an injection, it is there available. But there's others who feel as if a weekly subcutaneous injection, small volume, 31 gauge needle, isn't what you might perceive it to be, because we have this vision of what insulin therapy is with all of the complexity of glucose monitoring, which this does not require, and the history of people believing that because you're taking such a therapeutic, it implies that you're sicker than you would otherwise want to be. I personally, if I were taking the drug, would use the less frequent injection, but there is an oral form that is available, and there are registration studies ongoing right now with conventional small molecules that aim to mimic the single monoagonist. That means just GLP agonism, not the combination agonism that I shared with you. So it is quite possible, we shall see whether those successfully register, that there will be an oral, let's call oral tablet form of these drugs available to you.
Great, thanks. A question from Bill Whitaker, actually, who's on our my executive dean's advisory board. And I'm not surprised because this is a very detailed question. Does the glucagon component have any effect on fat cells, converting them into so-called white or metabolically active cells?
Yeah, so that is a great question, because in rodents, they're more prone to increased thermogenesis. There's more so-called brown fat. Bill would know this, some may not. Brown fat is more metabolically active, where white fat is perceived as being there simply to store your triglycerides. And so in rodents, I think that is absolutely correct, that the glucagon component is stimulating increased thermogenesis. Not as clear in humans, because brown fat is more controversial in humans, and I have not seen any clear evidence that the glucagon component is converting white fat to brown fat in any large way. But the efficacy is greater. And it is definitely catabolic. If used alone, it would be inappropriate because it breaks down large molecules, right? It causes lipolysis, it causes glycogenolysis, right? Breaking down your glycogen stores. And so it has to be balanced, buffered by an anabolic substance such as GLP-1, and better yet, GLP-1 plus GIP. And that's why I think the triple agonist may yet prove to be the best of these combinations. There is still reason to be questioning what will the effect be on the vascular system. It can increase heart rate. It seems to be greatest when you initiate therapy, and glucagon has an effect on the on the heart, right? So you just want to make sure that in long-term studies, we're not just improving body weight and metabolism, that we really are decreasing cardiovascular outcomes.
Yeah, thanks. T. Connolly asks, this is answered a little bit earlier, but it's sort of like, what would be the regular prescription? Would exercise, specifically weight training, be advised or prescribed with the intake of these weight loss drugs?
Yeah, I do think that some form of strenuous exercise that has been promoted for building lean mass and building bone mass, right, is advisable, particularly when you're setting out to lose as much weight as you see in the extremes. I think there's every reason to believe that there will be some degree of sarcopenia, loss of muscle mass, and some loss of bone mass, which is desirable to minimize or eliminate. In fact, there's quite a bit of pharmacology, ongoing medicinal chemistry, to see whether you can build into these molecules not only the ability to lower body weight, but actually stimulate those anabolic processes to defeat what otherwise is likely to occur.
If you give yourself too large a dose, and like regularly, like you're saying, can you lose a dangerous amount of weight? Like, can you drive yourself into anorexia, for example?
We've not seen that, right? So at toxicological doses, you don't cause a cachexia with this substance. It seems to be dose limiting as you get closer and closer to a normal body weight. It does, particularly the GLP component, has a profound effect on the gut, right? It slows gastric motility. And as a result, there is a very structured algorithm for how to get to maximally effective doses, where you'll use each week for a month, one dose, titrate up for another month, titrate up for another month, titrate up for a subsequent month, to try and generate a desensitization in the gut to the profound effect that it can have, that in many patients leads to a flatulence, excess gas, a nausea, and even profound vomiting. And that's why one has to be very careful not to be too aggressive with the dosing until you have reached what has been a registered appropriate use of these drugs.
Cecile Williams asks, does the site of receiving the shot matter in terms of weight loss?
Typically not, as long as you're administering it to the subcutaneous tissue, right? I don't believe these drugs have been registered for use by IV administration. They would have a long duration of action because of the binding to the plasma protein, notably albumin, but there is much greater likelihood for a burst early as you achieve higher plasma levels earlier. As I mentioned, semaglutide has been registered for oral use, but used each day, because what that does is it flattens the variability that occurs when you have such low oral bioavailability. So you're just dovetailing from day to day to minimize each day's variability. But it is highly inefficient way to deliver the drug.
Thanks. We have time for just one more question from Martha Perkins. This is a good one too. How long before insurance companies recognize obesity as a disease and cover these drugs for this use? And a corollary actually is, what makes these medicines so expensive?
Yeah, I can't answer the first one. I'd be completely out of my realm of expertise. Clearly, it reduces longer term costs by minimizing the risk factors that obesity represents to the vascular system and other organs. As far as the pricing of the drug, you might stay tuned next week. Bernie Sanders has a Senate hearing pertaining to drug pricing, and finding that sweet spot that incentivizes people to go and discover these spectacular drugs, knowing that eventually they will, a couple of decades, get to be generic substance at lesser cost. But giving people access to these drugs is of utmost importance. I mean, as I look back on the last 40 years, it's just unbelievable the transformation in our scientific capabilities to do what many people would have thought is otherwise impossible. Whether it was HIV, whether it was COVID, whether it's obesity. I mean, these are phenomenal advances. When I started, we were dealing with animal insulin, and we barely had glucose monitoring for treating diabetics. Think about how much more needs to be done. What is the molecular basis of a memory? That will come to be known, right? And with that will become profound therapeutics for treating cognitive dysfunction or even enhancing physiological function. So you can see that I'm very bullish about what we're capable of doing, and believe that we're just at the tip of the iceberg in taking biology, which has been largely a qualitative science, into quantitative biology, the ability to manage it in the way that, Rick, you would know physics, right? Mathematics and chemistry. And that's when you'll see the transformation, such that people will be wondering, can we manage longevity, as insane as that may sound at this point in time. So, bear with us. There are societal pressures. We want to make sure that people have access to these drugs, but how you find that right place is beyond me.
Thank you very much. Actually, just in closing, given that like of the more than 100 people that are connected here, a lot of us have the same bond, that it's IU alumni. Maybe just answer the question: what does IU mean to you, given your long connection, both as an alumnus and now?
Well, I'm here by choice. I've often joked that I'm a born again Hoosier, right? You can hear it in my Brooklyn accent, of which I'm quite proud. I'm not sure I knew whether Indiana was on the left side or the right side of Illinois when I were living on the East Coast, but I've grown in an affinity for this state and the just what we know as Hoosier hospitality. When you are on this campus, it's such a phenomenally stimulating place. Whether it's the athletics, swimming, basketball, soccer, whether it's music as you walk past the opera house, the auditorium, whether it's the history of the science here. Who isn't taking stannous fluoride right now, which was discovered right here, right? To those luminaries that I indicated, the Kinsey Institute. What a phenomenal place this is. You can't go walking it in the middle of January, but virtually any other time to just walk this campus is so aesthetically pleasing and intellectually stimulating of creativity that I can't say enough good things about Bloomington and this great university.
Great. Actually, that's holds for like a pitch for that. There's going to be the 50th anniversary of the discovery of stannous fluoride in Cress, actually later this semester, in the chemistry department. I believe that's going to be streamed. We'll make sure that gets out to this list. Also, just before we close, I want to also that Richard did this, but I want to echo it. I understand that Jack and Linda Gill are connected tonight, listening in on this talk, and they have been just generous donors to the college in Indiana University, and built, essentially enabled the building of the Gill Center that supports amazing science, just like Richard is doing. So again, thank you, Jack and Linda, if you're out there. With that, we can virtually clap a thunderous applause for Richard DiMarchi. And thank you very much for joining us this evening, and hope you have a good rest of your evening.
Great. Thanks again for joining us and participating in this evening's live stream. I would like to personally thank Professor DiMarchi and Dean Van Kooten for their time and expertise. We are grateful to you all. I would like to acknowledge that events like this would not be possible without the support of donors who understand the value of a liberal arts education. If you would like to support programs like tonight's presentation, or opportunities that connect alumni and friends with the College of Arts and Sciences, please consider making a contribution to the IU Bloomington College Alumni Engagement Fund at the Indiana University Foundation. Until next time, please take care.